Next we study the concept of power, which is the last topic in the chapter work energy power. How do we define power? Power gives us the rate at which a system does work. So by definition, power, which is denoted by capital P, is the rate at which work is done. Work is done. Okay. So mathematically then we say power is the rate of doing work, work done per unit time. So W by T should be the most basic definition, isn't it? Work by time, or W by T. Now understand that if we put up the total work over here and the total time in which that work was done, the power that we shall get here will be the average value of power. Over a total time period T, how much average power has been provided by the system, by the engine, by the machine, whosoever, whatever system is doing work for us. If we have to find out the power at a certain instant of time, then what do? We say that the instantaneous power will be a very small work done in a very short interval of time dt. So this becomes a more accurate definition of power than the instantaneous power we say is defined as dw by dt, the rate at which work is done. Now understand that dw, the small work done, can also be written as f dot dr, right? And when you divide it by dt, take this dr by dt together to write it as f dot v. Dr by dt is written as v. So we say that the instantaneous power, which is also written as just the power p, as f dot v. This is another formula that is generally used for calculating power for a given question. Okay, so this is the basic definition. If we come to the SI unit now, what is the SI unit of power? Can we say that the SI unit of power will be same as the unit of work divided by the unit of time? That will be a joule per second. This joule per second is called a watt, right? W-A-T-T, and written in short as W, capital W. So we say that 1 watt of power corresponds to 1 joule of work being done in 1 second. The more practically used units are a kilowatt, 1 kilowatt, which is nothing but 10 raised to the power 3 watts, right? And there's a horsepower also. Horsepower is another unit for power which we generally use. It is used in to find out the power of engines and all, the engines of vehicles and all, right? But that's not the SI unit. The SI unit is watt itself. Okay, so let's quickly take up a couple of examples to see what type of questions we get from this topic. So the first example is, there is a water pump which is rated 400 watts. So the power rating of the water pump is given to us, and it has an efficiency of 75%. It is employed to raise water through a height of 40 meters. Find out the volume of water drawn in 10 minutes. T is equal to 10 minutes. The situation is this: we have a certain height at which a pump is kept. This is, let's say, the pump P, and it is drawing water from a certain reservoir which is at a depth of 40 meters down over here. Okay, so this height is given to be 40 meters. From here, if this pump is pumping the water up with a power which is given to be 400 watts, and the efficiency of the pump is 75%. Now what is the meaning of the efficiency of the pump? Efficiency means the output power that the pump provides, which means the work that it does in a certain time for us, divided by the input power that it takes up in the process of working for us. So what is the input power for a pump? Generally it's the electrical power that we have to supply to the pump in the form of the electrical connection, right? We have to connect the wire of the pump into electric socket from where it gets electric power. and that power it uses to do work for us. So, if the input power is coming from the electricity and the output power is being given in the form of the work that the pump does for us, it is given that it works with an efficiency of 75%. So, it is only able to convert 75% of electrical power to mechanical power. So, from here we can find out the amount of power that it actually delivers while pumping the water up. So, can we say from here, according to the question, 75%, 75 by 100 is equal to the output power that we are really getting from it divided by the input power, which is given to be 400 watt. 400 watt is the electrical rating of the pump. So, from here we get the power output as 75 by 100 of 400 watts, which is nothing but 300 watts. So, it is this 300 watt that we are going to take as the power supplied by the pump. Okay. Now, going to the definition once again, can we say that the power by definition is the rate of doing work, dW by dt, which is d by dt of, understand that if the pump is pumping water up at a height of certain height h, can we say if m amount of water, m mass of water is being pumped up to a height h, the work done will be nothing but mgh by the pump, right? It is nothing but the rise in the potential energy of the water of mass m by a height h, so mgh, right? See that this can also be written as, because g and h both are constants, we can take them out, g into h into dm by dt. What is dm by dt? The rate at which a certain mass of the water is pumped up, the amount of mass pumped per unit time, that is dm by dt, right? So, see that from this particular expression we can write P is equal to dm by dt into gh, from where we can get dm by dt as P by gh. So, we can find out the amount of mass of water pumped up per unit time in terms of the power, g and h, which we can find out. We know all the three. 300 watts of power, g let us take as 10, height is given to be 40, and this comes out to be 3 by 4. What will be the units? Mass per unit time. In SI units it will be kg per second. So, what this expression is telling us is that the pump is able to pump up 3 by 4 kgs of water per second. So, we have got the amount of water pumped up per second. From here we can find out the water pumped per minute. Can we say the same value can be written as 3 by 4 into 60 kg per minute, right, which is 45 kg per minute. And we are supposed to find out in 10 minutes how much water is pumped up. So, 45 into 10 kg per 10 minutes, isn't it so? So, it is 450 kgs of water that is pumped up in 10 minutes by the pump. We are supposed to find out the volume of this water now. We know the mass. How to find out the volume? Volume is mass per unit density. We know that the density of water is 1000. So, 450 by 1000, that is 0.45 meter cubed. This much meter cubed of water is pumped up in 10 minutes of time. So, this is how we are able to find out through the power of the pump how much water is it able to pump up. That is the final answer. Let us take another question. The next question says a vehicle of mass m, is drawn by a constant power p. P, the power is given to be a constant. Okay. Express the instantaneous velocity v of the vehicle as a function of displacement s, assuming the vehicle to start from rest. The initial velocity of the vehicle is 0. V as a function of s is what we are supposed to find out. I am repeating the question. There is a vehicle of mass m which is drawn by a constant power p. Express the instantaneous velocity of the particle as a function of displacement s, assuming the vehicle starts from rest. So, let us start with a basic definition of power here. Power we know is given by F dot V, right. This power P is a constant, the left hand side is a constant. What about the right hand side? Can we write the right hand side as, the force can be written as mass into acceleration times V. Can we write the acceleration as, because we are supposed to find out the velocity as a function of s, we would try to express the acceleration in terms of s. So first thing that we can do is, we know that acceleration by definition is dv by dt, right, into v. But we don't want it in terms of t, we want it in terms of s. So what we do is, we use the other way of writing the acceleration, which is you write dv by dt over here and then you multiply with the ds and you divide with the ds, v remains as it is. And now you take this dv along with this ds and this ds along with this dt. So what we get here is m into dv by ds into ds by dt times v. This ds by dt is nothing but v itself, so we will get a v squared. So we get m into v squared into dv by ds. This is what we are getting as the power p, which is a constant. So let's write it once again. mv squared into dv by ds is equal to p, which is a constant. So from here, can we write v squared dv is equal to p by m times ds. See what we have done, we have taken this ds and this m on the other side of the equality sign. So what we are getting here is now an equation that we can integrate on both the sides. And when we integrate, the limits of integration would be when the displacement s is 0, the velocity of the particle is also 0. So the lower limits will be 0 on both the sides. Whereas when the displacement is s, let's say the velocity is some v. So v and s are the upper limits. Let's integrate this equation now. Integral of v squared dv will be v cubed by 3, and when you put the limits from 0 to v, you will get the same value actually. On the right hand side, p, m, n being constants will come out of the integral, and integral of ds will be just s from 0 to s. Solve. V cubed by 3 is equal to p by m times s, and from here now we can easily find out v. See that v comes out to be 3ps by m raised to the power 1 by 3. This is the required expression for speed of the particle as a function of s, its displacement, given the power and the mass of the body being constants.